Wednesday. Yeah, it is. Are we good to go? Good afternoon and welcome to one of the, I don't know if it's the last side event, but it's for sure one of the last side events here in this pavilion, and one of the latter ones at COP28 in general. We are running a little bit low on energy, and I think short of attendees by now, you will have seen that there are a lot fewer people certainly than there were earlier in the weekend and last week. So I will serve both as the first speaker and as the moderator of this event. We will be talking about the Global Greenhouse Gas Watch, which is a relatively new program. It is an intergovernmental program that was approved by the World Meteorological Congress in earlier this year. And it aims at getting us a better handle on greenhouse gas emissions and where they will be going in the future. And without that, parties cannot really do mitigation, which, as some of you will know, is what they are discussing right now. How aggressive do we want to be on this? What are we hoping to get out of it? And how do we bridge the global north-south divide on that? We're not going to get into that today. We'll talk about the science, and we will talk about how to use it more effectively in conjunction with some of the things that we have been doing already under the auspices of COP and the UNFCCC. I'll speak first. I'll tell you a little bit about what it is, and then we have Hiroshi-san Tanimoto from the NIES in Japan, who will talk a bit more about the science behind it. We have Tom Oda from USRA in the US, who will be talking about not about the Global Greenhouse Gas Watch, but how we align it with the inventories and activities-based estimation methods that we have been relying on so far. And then finally, we have Phil DeCola, an old colleague of mine, formerly from NASA in the US, who will be talking about how do we get this in the hand of the end users and what are they going to be doing with it. So if I could get the first presentation up, I will click my way through that and tell you what this is all about. So it is the Global Greenhouse Gas Watch, and I'm going to start with the problem statement. Why are we doing this? We are doing it because of a couple of weaknesses in the Paris Agreement. I mean, you've had the pleasure of being at the COP here, so you may have seen all kinds of holes in the Paris Agreement, and there are parts of it that are obviously difficult to implement. But I'll focus on two of them first. We all know that Paris was adopted aiming to keep the warming below a certain set threshold, and the tool that we have in our hands to accomplish that is dialing back the net anthropogenic greenhouse gas emission. Beautiful, simple statement, not simple to do. It is not simple politically and economically. This is what we heard a lot about yesterday. It is not simple politically and economically for the world's countries to do that. It is actually not that simple to even on a scientific basis tell them what to do. We heard again and again in the Majlis yesterday, the science is settled, the science is settled. It is settled insofar as we know that too much greenhouse gas leads to warming. It is not settled in the sense that we cannot tell parties, if you emit this much, these are the future concentrations that you will be looking at, and this is the kind of temperature that you'll be looking at. So there are some pieces missing. Parties know that, and this is, I think, one of the reasons why they have been relatively slow to take action. In a nutshell, the problem is that Paris focuses solely on anthropogenic emissions, which is good because this is what we emit and this is what we can control. But it's important to remember that nature puts in and takes out much more greenhouse gas than we do. What nature does responds to what we do in a way that is non-linear. And unless we understand that, we are absolutely flying blindly into the future in terms of what this will mean. The second problem that I want to briefly highlight is that We are sometimes using incredibly creative accounting methods when we try to explain what we are taking out of the atmosphere. You will have seen, many of you in the press, that the whole carbon market, the trading of carbon credits and carbon offsetting has come under immense flack. Because there is no universally agreed standard for this. Some of the projects are not particularly well defined. They are defined against baselines that may or may not be entirely justified. And the credits are not monitored in the future. The credits are actually not defined in terms of what they do to the atmosphere. They are defined in terms of what happens to the ground, whereas climate change is driven by this. Climate change doesn't care about emissions, it doesn't care about carbon credits, it doesn't care about emission inventories, it only cares about this curve. How much greenhouse gas is in the atmosphere? Doesn't matter who put it there or when. That matters hugely for the political discussions here, but it doesn't matter for climate change. Climate change only responds to this. And this is 60 years of growth of CO2 concentrations. If you want to really irritate people, you can put these timelines on it here. You can see Kyoto, you can see Rio, Kyoto, and Paris, and you can take them away again, and it doesn't matter. The curve keeps its march. So if you want to be really provocative, you could say, okay, so far what we've done in this context here hasn't really had the effect that we wanted it to have. I think that's the polite version of the take-home message here. How well do we understand that? This is a graphic from the Global Carbon Project, and we understand the top-level CO2 budget really well. Oops, that's not what I wanted to do. Does this work? Yeah. Okay, it doesn't work this way. The number over on the left is how much we emit from fossil fuel. We know that very well. The number in the red semicircle in the middle is how much of it keeps hanging around in the atmosphere. We know that very well as well. The difference between the number on the left and the number in the middle is the number on the right. So roughly speaking, we put in 40 billion tons of CO2 into the atmosphere every year. And nature kindly sucks out about 20 billion of those tons, and the other 20 hangs around in the atmosphere. We think that half of the half that is taken out roughly goes into the land surface, the other half goes into the ocean. We actually do not know that because we don't measure it. So we are flying partly on hopes and dreams here. We know that half of it goes out, but we don't measure when and where it happens. So the relative uncertainties on this part down here are very large. The lowest uncertainties in this whole CO2 budget diagram is what we emit in fossil fuels, but we don't know the other parts of the equation. So the take-home message from this slide is that currently nature is taking up half of what we emit. We don't know exactly when, where, or why that happens, and for that reason we cannot predict how long into the future this will continue. Both the reaction of the biosphere to what we are doing and the reaction of the ocean is highly uncertain. Okay, there's a picture hanging there that shouldn't be there. If we want to understand how CO2 concentrations change, there are basically two ways to look at that. First of all, bottom up, and this is actually the community that Tom is coming from. And this is what most of the activities that you will be hearing about in the context of COP and IPCC are based on. The logic is very simple. You take what you know or what you think you know that will alter the CO2 concentrations. The cows and the smokestacks and the cars and the planes and the cornfields and the forest and everything. Some of it puts stuff into the atmosphere, some of it takes it out. You add it all up and then you try to infer what might that do to the CO2 concentrations. This is very good for anthropogenic emissions. It's very good, especially in developed countries that have good national statistics that will let you do this. It tends to be delayed. It gives you bulk national data only in most cases, and they will be available with typically with a year or two of delay. The two main weaknesses are that it doesn't work well in developing countries, many of which don't have the data that will let them do this. It doesn't work well for most natural sources and sinks because nature doesn't report, so we need to measure it, and a lot of it we are not measuring. What the global greenhouse gas will add to this is, one final point. Since it's incomplete by definition, you cannot add it all up and get it to align with the growth curve because there are things that are missing. So you cannot verify how good your estimates are compared to the growth curve of CO2 because you already know that something is missing. What the global greenhouse gas will add to this is what we call top-down monitoring. It's not top-down in a political sense, it's top-down in a data sense. It starts from the atmosphere, looks at where do greenhouse gases, in this case CO2, come into and go out of the atmosphere based on atmospheric models and atmospheric observations and tries to disaggregate things that way. So now the movie that I started out with is gone. I actually wanted... Okay, the movie's simply not there. Never mind. This would have been a cool little animation that shows you how CO2 is really evolving in time like a weather system. You can compare that with observations and you can literally see where the CO2 come into and get out of the atmosphere. So now I hand wave my way through that instead. So in order for parties and for countries and other stakeholders to use that methodology as well, the WMO Congress earlier this year endorsed the Global Greenhouse Gas Watch, which is an internationally coordinated system that will use atmospheric models and atmospheric observations to give parties on a month-by-month basis geographically resolved information about where CO2 comes into and gets out of the atmosphere. It is very similar to the way that we do weather prediction and climate analysis. So the key elements are an integrated global observing system of greenhouse gases with open international exchange of observations, routine 24/7 modeling of what CO2 is doing, inverting that into flux estimates and internationally coordinated intercomparison of those flux estimates. So the main input is really these monthly estimates of where greenhouse gases come into, get out of the atmosphere, initially at a 100 by 100 kilometer resolution. We have the technical and scientific knowledge to do it at 1 by 1 kilometer. We just don't have the observations to do that yet, but it will come. The users are hopefully parties to the Paris Agreement. The reason why we are here right now is that we are trying to insert this as a key element of the second global stocktake. Those are the discussions that are going on now. SAPSTA recognized the importance of this in their meeting last week. So that was the first part of the reason why we are here. The second part is still going on now. Regional and local users will be using this as well. Phil is going to talk about that a bit later. There are players in the carbon markets who are extremely interested in this, in seeing whether they can use this methodology to shore up the carbon markets, who are quite fragile actually right now. So we have 190 governments that are behind this, 193 governments that are now behind this. Our aim here is to get recognition of it in the context of the Paris Agreement as well. So just to air a little bit of our dirty laundry, some of what we are not doing so well on yet is the density of observations. The top plot here is a weather map. The bottom one is a CO2 map, and you can see the scale of these fields are broadly similar. It's actually weather that drives the CO2, and CO2 drives the weather, so there's an interesting interaction there. But if you look at the density of the observations, what we have on the top is for weather, what we have on the bottom is for CO2. So we're missing about 2 orders of magnitude of observations, and we have ways to address that, and this is what we are working on here over the next couple of years. So the final slide here, emission inventories are good. And they are necessary because they tell us what we do and they tell us where we can act. They are not sufficient in and of themselves to crack this particular problem because they don't account for the whole the CO2 cycle. So in order for Paris to succeed ultimately, we will need to rely both on the bottom-up and top-down estimation methodologies. In order for carbon offsetting to contribute to this, which many people, there's not been so much talk about it here as there was perhaps in the last 2 COPs, where it was all about reforestation, afforestation, preserving rainforest, etc. If you want that to work, you absolutely need to monitor what it does to the atmosphere and not just count the trees and see how many of them are still standing. The third bullet here is something that the Valérie Masson-Delmotte, the co-chair of Working Group 1 on IPCC, said when we met in Kigali, a science meeting about a month and a half ago. She said something that not many parties here are fully aware of. Today, we are not able to tell you what your future emission scenarios would do in terms of future concentrations and therefore in future climate scenarios. This is a huge risk to the implementation of that, and that is really one of the main reasons why we need this to happen. And I'll stop talking here, and I think I'm going to hand it over to you, Hiroshi-san. I think we can just take the discussion and questions at the end. Thank you.
Good, great. So thanks for the invitation, and also thanks for the opportunity to speak our ongoing research, which we would like to most contribute to the policy processes, including nationally determined contributions, and also including GGGW or G3W, whatever, the WMO's initiative. So it's just great to be here and to speak about the contributions from NEAS, possible contribution and scientific research from NEAS, but not only limited to NEAS, but, wait a minute, oh, it doesn't work. Well, other national labs, which is JAMSTEC and NICT. JAMSTEC guys are here today. Yesterday, we had a Japan pavilion highlighting the importance of Earth observations in better quantifying emissions of greenhouse gases and also short-lived current forces. So today I'm going to give you some updates of the new satellite mission that we are pushing forward to be launched in sometime next year, soon, which is called GOSAT-GW. And we are aiming to contribute to these policy processes by better quantifying anthropogenic emissions of greenhouse gases. And I don't know. Yes, good. So first, let me reflect a little bit in the past, which we said GOSAT-3 satellite. So first one was launched back in 2009, and this is actually the first, world first greenhouse gases observing satellite. And second one was launched back in 2018, and like 5 years ago. And these are based on FTS spectrometry, like that. So GOSAT-GW, we're not saying GOSAT-3 because G stands for greenhouse gases, W stands for water vapor. So and it's like two sensors on the satellite. That's why, right? So we don't say GOSAT-1 because we never know. We never knew. Second one is coming, right? 2 is there, and 3 nobody cares. So first child is always appreciated, second child always complained, and third child, nobody cares. So that's the thing. So I have to also say that, what is that? Funding agencies is MOEJ, Ministry of Environment in Japan. And also MEX, which is the Ministry of Education, Culture, Sports, Science and Technology. So they did a lot of job. So that's really environmental agency and science and technology agency put together. And also JAXA and NEAS are working together. Okay. So that's an image of CO2 from GOSAT. Then, now GOSAT-2 is providing this image. So you can compare like this, GOSAT and GOSAT-2. So we are trying to make a better coverage of density of CO2 concentration and also methane concentrations from space. But still, you see the gap in the data, like last Peter said, these data coverage are not excellent enough for getting national emission estimates. Right? So it's getting better, but still scientists were trying so hard to get some information on national or country level emissions estimates. I'm taking the anthropogenic emission sources to compare with the anthropogenic emissions inventory. That's from satellite, and the top figure shows satellite, top left, And bottom left is models, so they compare satellite observations and model simulations to validate or verify emissions inventory are correct or not within some uncertainties. So I have to admit that many more scientists are trying, but this is a scientist at NICE, and they do this kind of comparison over the last few years, and still continuing. Then Paris Agreement has come, and that's really a great initiative for scientists as well, and also general public. That bottom-up approach for greenhouse gas emission reduction, which is NDC, is adapted, and therefore we believe we should bring science in this process. So GOSA GW mission is coming. Again, this is funded by Ministry of Environment mainly, and also I think for that it's sorry, big still coming. He likes me, Oshio. But okay, so 3 mission requirements we have. First one is to monitor 4 atmosphere global mean concentrations of greenhouse gases, like this left figure. I'm plotting GOSAT concentrations with ground-based observations, Mauna Loa, Hawaii, and South Pole. I can't see difference really, but that's really good because they're matching each other. Right? And second mission requirement is to verify national anthropogenic emissions inventory of greenhouse gases, which is CO2 and methane, or CO2. And third is to detect greenhouse gas emissions from large emission sources such as megacities or power plants, and permafrost for methane maybe, hopefully, ideally. But you can see from here that mission requirements are really having to better quantify emissions or verify emissions inventory at national or even city levels, like Tokyo or New York or Paris or Dubai maybe. So that's how GOSA GW, in particular we say Tanso 3 sensor, Tanso means carbon, is going to observe CO2 and methane and other species in the Earth's atmosphere, and we're going to observe CO2, methane, and NO2 as a tracer of combustion tracer of CO2. And the uniqueness here is we're going to measure these species at very, very high spatial resolutions, say 1 kilometer resolution. That's the really highest resolution in this kind of satellite observations for CO2 or even NO2 as well. So left panel figure shows how it's going to be observing CO2, methane, and NO2. And you see here 3-day global coverage, and green, red, blue is like a day 1, 2, 3. It's really mapping entire globe with the wide swath push blue mode. And still, this is still 10-kilometer resolution, which is still great. And also, right panel shows how we can switch observing mode. They have 2 observing modes. The one is wide swath push broom, and another one is optional, but it's a kind of high resolution targeting mode. This mode is going to have a higher spatial resolution, say 1 kilometer or 3 kilometers. 3 kilometers is promised. 1 kilometer is kind of an ambitious target, but we're going to try. So with that, GOSA GW, in particular Tanso 3 observations, is going to give you this kind of image. So you can compare the images of simulated concentrations from GOSA 1, 2, and this one. And that's actually methane, but you see here how dense the coverage is and over the land. We are going to even down to the country level, as I said, or even city scale, city level. And that's also simulated image of CO2, XCO2, and NO2 particle column density from on left and right over Japan. So you see here on CO2, little bit gradient high in Tokyo, Osaka, or Nagoya regions. It's like an industrial belt of Japan. But you see here in CO2 gradient, it's not easy to. It's not kind of drastic, right? But if you see NO2 distributions, you can more clearly see the enhancement of NO2 in Tokyo area, Nagoya area, Osaka area, over major city areas, and also industrial regions in So, sorry. No, so over Tokyo, that's really like this, and really CO2. It's not easy. CO2 is never easy, right? But NO2, it helps to identify where the sources, emission sources are located. We are going to even look at, as I promised, as I mentioned, individual large point sources such as power plants. So that's actually my picture taken from aircraft and over the power plants in Tokyo Bay of Tokyo, and simulated NO2 concentrations with inputting sensor specifications in a simulator. And then we're going to see, we could identify plant plumes from power plants. So that's kind of ongoing research we're making. So satellite is great. Those gives us a lot of information in terms of spatial coverage, variation, but without validation from the ground surface, it's just a gradient. So we are also putting so much effort in making a good, better, best, or ideally best quality of satellite data by enhancing validation capability. And of course, TCON, COCON, those ground-based remote sensing we are putting. But what's unique here is like we are putting instruments in a cargo ship measurements in collaboration with private sectors. So that's cargo ship, and they're keen. That's also, I think, important contributions between Tokyo and Kyushu. And it's like 3 days, really frequent measurements. And we're also operating other ships between Japan and US, Japan and Australia, Japan and Southeast Asian countries. CO2 and NO2 map here, and it's really showing plumes from urban cities. That's in situ measurement, but we are also putting, in collaboration with Heidelberg University in Germany, remote sensing instruments, CO2, methane, and NO2 on a cargo ship. So we really compare between ground or from ocean maybe, from the sea, and from the space. So I think with that, I'm going to finish my presentation, and I'd like to again highlight we are really willing to advance scientific research for science, but also for the policy processes, in collaboration with international partners. Thank you very much.
Thank you very much, Hiroshi-san, and we will proceed with Tom Oda, who will talk about inventories and what we in WMO call bottom-up estimation.
Right. Let's go out. Should I just... Right. Okay. Right. Hi, everyone. I'm Tom Oda. Thank you, Peter, for invitation. I am a senior scientist at the University Space Research Association. It's a non-profit organization in Washington, D.C. I also affiliate with the UMD, also the Global Environment Measurement Monitoring Initiative by Optica and also IAGU. And I'll be speaking about, as Peter said, bottom-up, but this is something that he told me a couple of days ago, bottom-up, top-down approaches. So this is my topic today. So hopefully I can help the fostering conversation more based on the two speakers before. So my message today is really pretty much this. As Peter, you said bottom-up or top-down in your slide, but my message bottom-up and top-down approaches. Then some people say sometimes versus. I think I admit when I'm a student, probably I put BS. And like comparing to, we get number from bottom up, like inventory. Or here we just not just the inventory, but more like the calculation using some activity level data from surface. And what could be remote sensing versus something estimated coming from atmospheric data. It sounds like we are trying to, hey, you're wrong, we get this number, you get this number, hey, why we are not matching each really well. That's kind of conversation I haven't been seeing in my career. But this is not that time. This is really old-fashioned way, I would say, to see this thing. I got two figures here. Those are from National Academy and U.S. National Academy report. I contributed last year. I got a little information here if you're interested. But this is really interesting. In a conversation among community members, it's really difficult to capture about the methodologies available to us right now. It's not just simply inventory versus the emerging model or simulation. Very, very diverse. And think about it, we just not mentioned estimate, but if you're sort of broadening definition as information of greenhouse gas, then you can really expand the methodology available to us. It's really difficult, but we gave a try. And one is actually, we don't say bottom up, but I would say activity data based. So what I mean is that we basically calculate emission based on the activity level. Emissions are proportional to activity level, which is pretty simple. Then with definition, you can broaden the definition a little bit more. The inventory, obviously, if you're looking at energy emission from energy sector, you collect the fuel consumption or something else, then multiply by emission factor. If you're really interested in traffic sector, you might count the number of cars. If you're interested in agriculture or dairy, then you might count the number of animals. Then you can multiply the emission factor or maybe conversion factor. We can do that number. Then for the last period, I mentioned that this is also an important approach to produce greenhouse gas emission. And particularly this activity data approach, because you know what the sort of sources or driver you are interested in. So you particularly collect the activity level for this particular purposes. So you can get the estimate from the source of your interest. This is a great way to do it. So you can really directly respond to the needs. For example, if you look at the emission inventory, emissions are reported by sectors, then you can realize, oh, I want to reduce emission from this sector by X%. This is pretty possible, pretty straightforward. That's why it has been probably more maybe not everyone, but in general, popular to policymaker or some of the planning for emissions. Then we are in the WMO. We're talking in this initiative. We are talking about more the emission based on atmospheric data, which is on the right. And this is also not just inversion or assimilation. We have so many, like Hiroshi mentioned earlier. We have so many variety of data set from atmosphere, surface, also space, you name it, many information. But the fundamental thing is here is using atmospheric data. So this is kind of interesting. If you see this plot, hey, is that the emission from that 5 years? It's not really like dividing two things. But the key thing is that we are trying the atmospheric data. It really plays a key role in this estimation. And obviously, because from atmosphere, you can get everything. So like the Peter mentioned earlier, we see the atmosphere, so you can see all the emission happening. Then we can look at the emission sort of gases you put in the atmosphere. That's really the key thing to do this. And obviously, that's great. But at the same time, if you really wanted to look at this particular sources, this might be really difficult. The same thing might be for the country as well. Maybe that's something we have to do a lot of improvement anyway. And great. So I just wanted to do more schematics. This is a very short talk. I don't have much slide here, but I'm trying to trying to back up what I said in the earlier slide. On the right-hand side, we see the atmosphere. Like we have so many processes. We burn fossil fuels, and hopefully not in the future, but produce CO2. Then we have some activities like agriculture, and we drive a car. So many processes. If you do the activity data float, you can look at the particular activities. Oh, okay, maybe counting the sort of area of agriculture, how expanded, or some of the cows, or you can see there also the fire as well, and those are some of the processes. But if you look at atmosphere, everything. If you see so many arrows going up to the atmosphere, then what you see is actually probably one number, okay, like X ppm, and how you can go back to it. So this is why this is not just the and or versus, but we do need both. And I just wanted to come some picture because I thought maybe the movie not gonna work, so I just put that little caption here. But we USLA supported NASA to go to the activity, and you might see this sort of movie version of it on the social media. But it's about one of the things we can do is concentration monitoring. We put the OCO2, NASA's OCO2 satellite data. Then we can do the assimilation. We can estimating the state, not just emission, for example. Then you can monitor the concentration. But again, just the entire atmosphere. Maybe we can sort of answer the question like how much CO is going up or going down. That's the question. If that's the question, we can directly answer to it. But we need more steps to do it because we need to use those information to action. And this bottom one is also I'm pleasure to contribute this work, but we did the inversion based on the OCO2 data. Then this one we also have a movie, but this one doesn't move. But this is also the country-based emission. So this is particularly useful because we see the atmosphere, so it's already getting tricky. If you look at a small country, maybe a little bit tricky, if you think about a particular sort of emission sector within the country, it might be difficult. But this is kind of great demonstration that we can help out. They think about the amazing systems that are being developed in the research community, but that's not really available to everyone. If you look at some of the countries still developing, doing capacity building, for example, while we are waiting, there being systems that are being developed, we can help out. Hey, this is the mission that might be happening in the country. Also think about going back to the emission inventory. Usually we say the emission inventory is not really aligned with the atmosphere, but usually that's national emission. We also develop emission inventory research community. That is usually more close to the CO2 growth rate or the CO2 changes. But again, in the reported emissions are mostly focused on anthropogenic emissions, so it's maybe not the sum up to the CO2 emission growth rate we see in the atmosphere. But this is really helpful to going back. Then maybe I'm just talking too much about CO2, but think about the methane. Usually we know the processes in emission inventory because that's why we apply the activity data approach. But for example, unintended emission, like, oh shoot, methane leaking, that's not an emission inventory. Then that's something the atmosphere measurement really help us to identify, oh, this is something we need to work on. Then potentially we can embark some action to climate change. So then this is my last slide. Then I just wanted to leave you this, probably one of the conclusions for our report. This is a hybrid approach. Then this is really, personally, I had a I really enjoyed the discussion about this. But again, this is not like a bottom-up or top-down, but we really need to combine two things. Then by meaning combining, it's not just that, if you're doing coding, it's not just combining two models or just transferring information to, different systems, but more organically combining information. And like I mentioned earlier, for example, if you do the inversion or, basically that's a combination of previous figure, but the arrow is really going different direction. Then you can really think about not just the emission or concentration, but I think information to be used by stakeholder or policymaker, then think about you can learn within the system. So this is not just a numerical system, but more like let's say the information generation system. So we should keep in mind, this is kind of we should be doing. Then again, we have so many ways to produce greenhouse emissions, so it's a really exciting time. So we really fully utilize the available data, also technology we have today. And I think GW, D3W is a kind of probably first realization of a hybrid system. So I'm very excited to be part of this. Thank you so much.
Thank you very much, Tom. Phil, you're the last one up. Tell us how policymakers are supposed to try to make sense of this, or also you are working also at a more local scale, not just with national government, but even subnationally.
Thank you, Lars Peter. Yeah. So another way of saying what my colleague just said is that the GGGW and the IGUS initiative, which I'm going to tell you about, are sort of brother and sister initiatives. And going back to the beginning of the IGUS initiative, which was right around the time before the Paris Agreement, it was around the time of COP28 in Lima, Peru, that set the stage for NDCs. At that time, we had still been facing the fact that when you talked about the scientific inputs, as Lars Peter already said, the Keeling curve was the cause for concern, especially when you were able to correlate it with the temperature rise. And the negotiator said, thank you very much, scientists. We'll take it from here. But then the door got opened a little bit in terms of climate services coming into vogue. But those climate services were bringing science in only for impacts and adaptation on that side of the equation. It was only recently that we started to gain acceptance for the science coming back in to guide the solutions on the mitigation side. And this is what's really exciting. And so there's the negative statement, we can't manage what we don't measure, but the good side of that is we can manage what we do measure, and we need that kind of management. As Lars Peter said, the devil's in the details, and we can see we have a problem, but we really don't know how to get out of the trouble that we're in. And that's why these GGGW and IGUS are critically important, and they really are sort of ham and egg working together. And I'm going to tell you a little bit about that. Everybody has seen already, okay, oh, sorry. Can somebody help me? There we go. Okay, so hit the right button? Okay, thanks. So you've seen this a bunch of times before, and the answer to the question of why we have a Paris Agreement, as you've already seen, is this rising abundance of CO2 and the relationship to the temperature record. But a couple of more detailed points. Lars Peter pointed out how we don't understand why we get this 50% benefit, half in the ocean and half on the land. It's worse than that, because when you look at the rate of change of concentration of CO2, in other words, the second derivative, you see all these wiggles have meaning in them, and that tells you that, yes, on average, we're having this 50% benefit, but some years it's 90%, other years it's 10%. There's interannual variability that we have no clue what's driving that. And that's another, and then the other point is CO2 is not the only greenhouse gas that humans are putting into the atmosphere. It's the big one, but we have similar curves for the whole basket of Kyoto gases. Only the ones with both sources and sinks, both biogeochemical and anthropogenic from thermospheric, the burning of fossil fuels, have this wiggle. The rest are just geometrically rising, like the HFCs that were being handled now in partnership between the UNFCCC and the Montreal Protocol under the Kigali, and then we have methane and NO2, N2O, I mean, and a number of other gases that are all showing this geometric rise and additional cause for concern. And so the relationship between GGGW and IGUS, in fact, when we initially, back in 2014, 2015, started to get approval to go ahead with the concept and planning for IGUS, what we realized the need for GGGW at the global scale, but we saw at first we really needed to get our foot in the door here, like I told you before. We needed to get science back in the door for guiding solutions. And so we said, let's focus on mature research capabilities that marry to, at smaller scales, as Lars Peter said, to real mature decision making. And so we were able to start on that process, and we established some principles for these scientific services. As Tom already said, we were very gratified when the Academy reinforced what we said when we originally wrote the IGUS plan, was we need a hybrid approach. It's not the us versus them, top-down versus bottom. It's let's add this new valuable constraint piece of information to improve our estimates and target and track the emissions and determine whether the policy measures are having the effect that we want. And really, one of the other key things that we're proud of in IGUS is we recognize the only way to do that is we can't hand it over to the users as scientific information. If the information is going to really be used for action, for mobilizing action, you need to sit and figure out what language it has to be in. How do you really convert that into something that can guide decisions? So we sit at the beginning, not at the end. We don't throw the information over. We start with the users at the table. And we need standards. We need the standard approaches so that it's a level playing field from country to country, city to city. And we want to really focus, again, like I said, on where we have the opportunity to move the needle, where we can really have true additionality, that the scientific capabilities, the research successes are being matched up to something that's really additional, meaning it was needed to make that emission reduction happen. So, as you see here, the original 4 objectives have here still a global stocktake application, but we had to wait for Lars Peter to come along after we tilled the ground here with these other things to get people hooked on atmospheric composition contributions to this thing. So we started with support, collaboration in a hybrid approach with those inventory compilers at the national scale. We also recognized the subnational need. I mean, there was more ambition in some respects, and they have their hands on more levers of emission reduction at the subnational city scale. And then also we focused on facility scale, industrial scale, especially with regard to methane. And here, now I'm just going to wrap up with a few examples. So here's an example of the kind of things that IGUS really promotes and tries to codify the skill for. this was some work that was done by my colleague Riley Duran, led by my colleague Riley Duran from the Jet Propulsion Lab, where they took a spectrometer, an airborne spectrometer called Avarice, and they did a California survey of all the different sources, point sources, super emissions of methane, to really kind of see where California was at with their assessment of methane emissions for the state of California across oil and gas operations, waste management, and agriculture. And what they found was extraordinarily important and interesting, that a large part of, in fact, half at least of the California's emissions come from these large point sources, and the other half from the diffuse sources. But then that half is coming from very, very few pieces of infrastructure across those sectors that I just mentioned. And they're responsible for a very large chunk of the methane. And what's really cool about it is when, this was not even a mitigation effort, when this information was delivered to some of the owners of these emissions on a voluntary basis without rules and regulations, there was a reduction in California's methane emissions over the next few years that was significant, just based on informing people and with no rules or regs, just voluntary action. That's the power of this information. And as Tom showed, you know, the state of the art that we've been depending on since the beginning of this process, the protocol led by the IPCC Task Force on National Inventories, is basically, you know, as Lars Peter showed, for CO2 it's pretty good, where you count up the smokestacks, you count up the power plants, you count up the vehicles, and you multiply by emission factors, and you get a pretty good number. But for methane, for HFCs, and for SF6 and other gases, the skill level drops significantly, and so we really need to bring that atmospheric layer in. And you can see an example of that here. One of the pioneering countries in using this kind of information that was foundational for IGUS is the UK. They've been for many, many years, going back to the 90s, comparing what does the atmospheric conversion tell us versus what the bottom-up activity data emission factors. And you can see here, starting the blue in 2013, this is for the gas HFC 134A. It's a mobile refrigerant. It's a very important, powerful greenhouse gas, thousands of times molecule for molecule more warming potential than CO2. And you can see that here, the red curve is the atmospheric conversion with its error bars you can see in the pink here. And then the blue, green, and yellow were the preceding years, and then the most recent year, which was 2022 that I have here, are these bars. And you can see that over time, through a partnership, which is true, none of this is true, but through a partnership and looking at all the information together, the inventory compilers were able to go back, adjust their emission, check their emission factors, check their activity data, and as a result, each year, working together with the atmospheric scientists, they've improved the agreement between the two. And it's sort of like a guide. It's sort of just a pointing, and it's really a relationship and trust that has to be between the two groups to get this progress. One of the other objectives that we have is for urban, as again, because people glibly will say more than 70% of fossil fuel CO2 emissions come from large urban domes of activity, and they only cover around 2% of the land area, and they're responsible for that large amount across the three scopes, scope 1, 2, and 3. Scope 3 being consumption-based, 1 being direct emissions from the city, and 2 being upstream from power plants outside of the city. And you can see that what we're able to do here is where the levers are, where the action is, where you building retrofit projects can really reduce emissions in a city, or a low emission zone in a certain part of the road segments of a city could really help reduce emissions. What we really need to do is take the atmospheric data, which we've done, and compare it to the kind of thing that very, very granular inventory, building by building, street by street. So this is, again, is a partnership, and we benchmark these kinds of very high resolution, accurate, consistent city inventories that are maps, not just numbers in a pie chart. They're mapping building by building and street by street and benchmark to the atmosphere. So in general, what we have here is this partnership between GGGW, which is going to be able to get agreement between all the groups around the world who are doing global flux determinations with a wide suite of measurements, increasing those number of measurements by this initiative, getting skill agreements between all the groups, not homogenizing the efforts, but getting agreement on what the skill we should expect, and then handing off and post-processing with the IGES initiative to really deliver to the users in the language that they understand so that we can target opportunities to reduce emissions and track the efficacy of those policy measures. Thank you.
Thanks very much, Phil. So this is what, come on up here. I mean, we have sort of an equal split between audience and panelists here, so that's interesting. So this is what the scientific community is trying to inflict on the people who are now discussing it. And we will have had some successes. Somebody just slipped me the agreed text on the global stocktake, and they are not quite ready for this yet. SAPSTA is ready for it, and maybe we will be ready to discuss it at the global stocktake next year, but apparently not this year. Tom, I completely agree with you. It's not either or. We will need both. We will need both, that's clear. The activity data on the ground tells us what we think we are doing. The atmospheric data tells us what we and nature are doing together with the atmosphere, and then it's up to us to disentangle that and tell policy makers what we need to do better. I don't know, are there any comments or questions for any of you who are listening to this?
Don't be shy.
Yeah.
Okay, so why should these people care? You're working with the NDC partnership here, and they're working with dozens of countries who are trying to write, or going to be writing. Right now, they're trying to implement their existing NDCs. But in 3 or 4 years, they're going to start writing their next set of NDCs. And then 5 years after that, they'll have to write another. This is a process that's going to go on as long as climate change is an issue, which is going to be for a while. What are you going to offer these guys down the road that will help them write better NDCs and also help them with their carbon markets?
I have the microphone, so I'll go first, and then I think probably each of the other panelists will have something to say about this. So the NDCs should determine, or actually should define what are we, you add up all the NDCs, and that's our collective ambition on what we're going to do better. Right now, we can't tell national government what that ambition should be. That was the point I started out making initially. We cannot tell you that you should have your emission and then the following will happen. We actually don't know. So where the G3W is very different from what Phil was talking about is that we actually try to understand the whole carbon cycle. IGES is a lot better than G3W at pinpointing emission, which is one part of it, because it's localized. The really difficult problem is to how to tie the whole thing together. What the rainforest and the kelp forest and the ocean does is not localized, and IGES cannot do that. And we need to do that, otherwise the NDCs won't mean much.
That's really true. Another point of emphasis of what Lars Peter just said, in fact, is that we can't just throw our hands up and say where these diffuse natural processes are taking place, and as the world warms, they're increasing their emissions. We can't just say, oops, we can't do anything about that. We need G3W to guide what we can do about that. And I love your question, Bonnie, because before I was invited to be on this panel, I came by here the other day because I love the NDC partnership, and I was talking with Molly, who also lives and works in Washington, D.C., and we've agreed to sit together because it's a big opportunity for IGES to really look country by country, partner by partner, at where we can help both enhance their NDCs and then help them see where they're going, see where their progress is. So I look forward to seeing you back in DC, Molly.
Okay, we just got a warning from our organizers, so 1 minute for each of you. Why does the NDC care about this?
Right. I'll be very quick. Because now we have 1.5 degree goal. So NDC is not really connected because what you do is really
how to get in a 1.5 temperature. So you really need to know your contribution within the system. So that's why we really need a system like G3W or even IGES. I think that's the best thing we can offer from science.
COP29. Thinking is good. It's not illegal yet.
Oh, really? Well, it's really kind of, well, we should keep going, keep thinking about that. All right. And yes, atmospheric observation, like Peter said, I'm kind of personally impressed. Peter said the carbon CO2 is not easy, but it's kind of easiest. Not the easiest, but it's, other species are more difficult, I would say. That's right. So that's something.
Thank you very much. I somewhat disagree with you. I think the others, I mean, so China and the US came out with a joint declaration on what they wanted to do with greenhouse gases, and it covered everything except CO2. That tells you that it's probably not the easiest. It's policy-wise, it's certainly not the easiest.
And really, I'm sorry for that misunderstanding, because really what I was saying is that in terms of understanding the rise in the emissions and where to attribute them, it's harder. But doing something about it in many cases is easier, especially for methane. We have low-hanging fruit there, and that's something that we have to win the race to 2030, or there won't be any 2050, and we can do that by going after that 50% of super emission point sources with the efforts like I showed you here, and now some satellite efforts looking for those plumes as well.
All right, I think time is up. Thank you very much, Hiroshi-san, Tom, and Phil, and thanks to you brave soul who hung out with us here until the end. Let's go over and hear what they've come out with at the COP plenary, which is about to start. Thank you very much, and thanks to the NDC partnership for hosting us.